Welcome to the deep dive. Today we're tackling the wild world of software design and deployment. We'll be using the book Release It, Design and Deploy Production-Ready Software as a way to kind of understand what it takes to create software that, it doesn't just work, but it thrives out in the real world. I think most people have experienced that moment when an app crashes or a website freezes at the worst possible time. Ever wondered what causes those tech meltdowns? That's exactly what we're going to explore.
That's right. This book isn't just about, lines of code. It's about understanding the bigger picture of how software interacts with the real world and how seemingly small choices can have huge consequences.
Okay, so the book starts with a story that really grabbed my attention, the Core Facilities Project. An airline spent millions building this new super robust system, but then a tiny programming error during a routine database switch ended up costing them a whopping $17 million in downtime. What exactly happened there?
So this airline was moving to a more modern, flexible system. They built this core facility system with redundant servers, backup databases, and even a separate backup site miles away. They thought they had planned for everything.
Sounds like they had all their bases covered.
They thought so. But during a planned database failover, a tiny error in how the system handled database connections triggered a domino effect. Think of it like a single loose screw in a bridge. It might seem insignificant, but under enough stress, that one tiny flaw can cause the whole structure to collapse.
And in this case, the bridge was the airline's entire check-in system.
Exactly. The kiosks crashed, the phone lines went down, flights were delayed, and passengers were stranded. All because of this one tiny error that spiraled out of control.
$17 million in downtime. That's a hard lesson in why stability matters.
It really is. And the book introduces this idea of stability antipatterns. These are common design and development practices that can make systems vulnerable. Neglecting these anti-patterns is like building a house on a shaky foundation. It might look okay for a while, but the first sign of trouble and the whole thing could come crumbling down.
Okay, let's dig into these anti-patterns. The book mentions circuit breakers as one pattern to avoid these issues. Can you walk us through what that means and why it's so important?
Imagine your house has a power surge. Instead of the surge frying all your electronics, a circuit breaker trips, cutting off the power to that circuit and preventing a larger disaster. That's what a software circuit breaker does. If one part of your system starts malfunctioning or gets overloaded, the circuit breaker isolates that component, prevents the issue from spreading, and allows the rest of the system to keep running.
So it's like damage control, containing a problem before it takes down the entire system. Can you give us an example of how this plays out in real life?
Think about a large e-commerce website during a big sale. There's a huge spike in traffic, and one part of the system, maybe the payment processing module, starts to slow down. Without a circuit breaker, that slowdown could cascade, affecting other parts of the website, like product browsing or shopping carts. Eventually, the entire site could crash, leading to lost sales and frustrated customers. But with a circuit breaker in place, the system would detect the issue with the payment processing module and temporarily isolate it. Customers might experience a slight delay in processing their payments, but the rest of the website would continue to function normally.
That makes a lot of sense. It's about anticipating potential points of failure and building in safeguards. So circuit breakers are like those emergency exits in a crowded theater. They might not be used often, but they're essential when you need them.
That's a great way to put it. The book goes on to highlight other stability patterns that help prevent these cascading failures.
Let's dive into those. What are some other common anti-patterns developers should be aware of? And what are the stability patterns they can use to build more robust software?
Well, another common anti-pattern is neglecting to implement proper timeouts. You see, when one part of a system needs information from another part, it often has to wait for a response. If that response is delayed or never comes at all, the waiting component could end up hanging, indefinitely consuming resources, and potentially bringing down other parts of the system.
So it's like calling a customer service line and being stuck on hold forever, except in this case, it's your software that's stuck.
Exactly. And that's where timeouts come in. They're like setting a limit on how long you're willing to wait for that response. If the response doesn't come back within the timeout period, the system can take action, perhaps trying a different approach or simply log in the error and moving on.
So it's about preventing one slow or unresponsive component from holding up the entire show. Are there any real-world examples of where this might be critical?
Imagine you're booking a flight online, and the system needs to check seat availability with the airline's database. If that database is slow to respond without a timeout, you could be stuck on that booking page staring at a spinning wheel unsure if your request is even being processed. With a timeout in place, the system could either try again, offer you alternative flights, or at least give you a clear message explaining the delay.
It seems like timeouts are all about setting realistic expectations and having backup plans. What other stability patterns should developers keep in mind?
Another crucial one is the concept of bulkheads. Think of it like the compartments in a ship. If one compartment floods, the bulkheads prevent the water from spreading and sinking the entire vessel.
So it's about isolating different parts of the system so that if one fails, the damage is contained.
Precisely. In software, bulkheads are used to isolate critical resources or functionalities. For instance, you might have separate thread pools for handling different types of requests. If one type of request starts to overwhelm the system, it won't impact the other thread pools, and those functionalities will remain available.
So it's like having separate lanes on a highway. Even if there's a traffic jam in one lane, the other lanes can keep moving. What are some other key stability patterns we should know about?
There's fail fast, which, despite the name, is all about making your system more robust.
That sounds counterintuitive. Why would you want your system to fail quickly?
It's about detecting errors as soon as possible and handling them gracefully rather than letting them fester and potentially cause more damage down the line. It's like noticing a small crack in your windshield and getting it repaired right away rather than ignoring it and risking a larger, more dangerous crack developing.
So it's better to address a problem head-on than to let it linger and potentially cause more harm.
Exactly. And there are a whole bunch of other patterns like handshaking, which ensures clear communication between different parts of the system, decoupling middleware to reduce dependencies, and test harnesses to simulate failures and test the system's resilience.
It sounds like building stable software is as much about anticipating what could go wrong as it is about writing clean code. But stable software isn't enough, right? It also needs to be able to handle the demands of the real world.
You're absolutely right. And that brings us to the critical area of capacity planning and performance.
Perfect. Let's dive into that next. We'll be right back after a quick word from our sponsors.
Busy.
Just kidding. We're keeping this deep dive going without any interruptions.
All right, so we've talked about building software that's, stable and can handle those unexpected hiccups. But let's face it, in today's world, software isn't just running on a single computer tucked away in a corner. It's out there connected to networks, databases, other systems. It's a whole interconnected ecosystem.
You're hitting on a key point. It's not enough for software to just work in isolation. It has to function seamlessly within the complex environment of a data center.
Data centers are those mysterious places where the internet lives. What are some of the things developers need to consider when building software that's going to be living in a data center? Well, one of the biggest considerations is capacity planning. Data centers are designed for efficiency, but they have limitations. You need to understand how much data you'll be storing, how much network bandwidth you'll need, how many users you'll have. If you don't plan for these things, you could end up with a system that's constantly overloaded and underperforming.
So it's like planning a big party. You need to know how many guests are coming, how much food and drink to buy, and how much space you have.
Exactly. And just like with a party, if you underestimate your needs, things can get messy quickly.
The book mentions some common capacity killers, things that seem small but can have a huge impact on performance. What are some examples?
One common culprit is bloated sessions. Imagine you're shopping online and every time you click a link, the website stores a ton of information about your browsing history in your session. That session data takes up memory on the server. Multiply that by thousands or millions of users, and you can quickly overwhelm the system.
So it's like carrying around a huge backpack filled with unnecessary stuff. It slows you down and makes it harder to move efficiently.
That's a great analogy. Another capacity killer is wasted bandwidth. Think about sending a large file attachment via email when a simple link would have sufficed. You're using up more bandwidth than necessary, which can slow down the network for everyone.
It's like taking up 2 parking spaces when you only need one inconsiderate and inefficient.
Exactly. And then there are database nightmares. Poorly designed databases can be massive performance bottlenecks. Imagine searching for a book in a library with no card catalog or organization system. It would take forever. Similarly, an unoptimized database can slow down queries and make the whole system crawl.
So it's about working smarter, not harder, right? Designing systems that use resources efficiently.
Absolutely. And one of the best tools for improving efficiency is caching.
Caching. What's that all about?
Imagine you're baking a cake and you keep having to go back and forth to the pantry for ingredients. It would be much faster if you had all the ingredients you needed laid out on the counter in front of you.
Right, that's the mise en place technique, right? Chefs swear by it.
Exactly. Caching is like mise en place for software. It's about storing frequently accessed data in a faster, more easily accessible location. So instead of going all the way back to the main database every time, the system can retrieve the data from the cache, which is much quicker.
So it's like having a cheat sheet or a shortcut.
hmm
But the book mentions that caching can also be tricky. What are the pitfalls?
The biggest pitfall is caching the wrong things or caching things for too long. If you cache data that rarely gets accessed, you're wasting valuable memory space. And if you cache data that changes frequently, you risk serving up outdated information.
So it's like keeping a stale loaf of bread in the pantry. It might have seemed like a good idea at the time, but it's not doing you any good now.
That's a perfect analogy. Effective caching is about striking a balance between speed and freshness. You need to carefully consider what to cache, how long to cache it for, and how to invalidate cache data when it becomes outdated.
Okay, so we've got stability, capacity, and now caching. Are there any other major considerations when it comes to building production-ready software?
Well, one area that's often overlooked is garbage collection.
Garbage collection. Sounds like a chore. What's that all about?
Think of it like this: as your software runs, it creates objects in memory, like temporary variables or data structures. When those objects are no longer needed, they become garbage. If you don't clean up this garbage, it can accumulate and eventually consume all your available memory, leading to performance issues and even crashes.
So it's like leaving dirty dishes in the sink. A few dishes aren't a big deal, but if you never wash them, they pile up and create a real mess.
Exactly. Garbage collection is the process of automatically identifying and reclaiming this unused memory so your system can keep running smoothly.
So it's like having an automatic dishwasher that takes care of cleaning up after you.
Precisely. But just like with a dishwasher, there are different settings and cycles that can affect how efficient the garbage collection process is.
What are some things developers should be aware of when it comes to garbage collection?
One key consideration is the choice of garbage collection algorithm. Different algorithms have different trade-offs in terms of speed, memory overhead, and pause times.
Pause times. What are those?
Well, sometimes the garbage collector needs to pause the execution of your program for a short period to perform its cleanup tasks. These pauses can be noticeable to users, especially if they're frequent or long.
It's like when the garbage truck comes and blocks your street for a few minutes. You have to wait for it to finish before you can continue on your way.
Exactly. And just like you wouldn't want the garbage truck to block your street every 5 minutes, you don't want garbage collection pauses to interrupt your software's performance too frequently.
So it's about finding the right balance between keeping things clean and keeping things running smoothly.
Precisely. And that's where careful tuning comes in. Developers can adjust various parameters to optimize the garbage collection process for their specific application and workload.
It sounds like garbage collection is one of those behind-the-scenes processes that we don't often think about, but it plays a crucial role in keeping our software running smoothly.
Absolutely. And it's a great example of how building production-ready software is about paying attention to details that might seem minor, but can have a big impact on overall performance and reliability.
Okay, so we've covered stability, capacity planning, caching, and garbage collection. What else should developers consider to make sure their software can handle the real world?
Well, we've talked a lot about the internal workings of software, but let's shift gears and talk about how software interacts with the outside world. That's where networking comes in.
Okay, let's dive into that. We'll be right back after this quick message from our sponsors. Just kidding. We're sticking with this deep dive, no interruptions, just pure knowledge flow. All right, we're back, and we've covered a ton of ground so far. Stability, capacity planning, caching, even garbage collection. Who knew there was so much to think about when it comes to building software?
Yeah, it's like an iceberg. What you see on the surface, the app on your phone, the website you're browsing, it's just a small fraction of what's going on beneath the surface.
Exactly. And speaking of things beneath the surface, we're about to dive into a topic that's often shrouded in mystery networking. I'll admit, this has always seemed a bit like magic to me, data just zipping around the world, somehow ending up in the right place.
Networking is one of those things that we take for granted until it stops working. Then suddenly we can't send emails, browse the web, or watch cat videos, and we realize just how much we rely on this invisible infrastructure.
So true. But what does networking have to do with building production-ready software?
Well, in the real world, software rarely exists in isolation. It needs to communicate with other systems, access databases, retrieve data from remote servers. All of that happens over a network. And just like any other part of the system, the network can be a source of bottlenecks, delays, even failures.
So it's not just about writing code that works. It's about writing code that works reliably over a network that might not always be perfect.
Exactly. And that means thinking about things like latency, the time it takes for data to travel across the network. If your software is making a lot of network calls and the network is slow, it can significantly impact performance.
I've definitely experienced that, like waiting for a website to load or for a file to download and just wondering if anything is actually happening.
Exactly. And then there's bandwidth, the amount of data that can be transmitted over the network in a given amount of time. If you're trying to send a large file over a slow network connection, it's going to take a long time. And it could even cause congestion for other users on the network.
So it's like trying to fit a large truck through a small tunnel. It's going to be a tight squeeze, and it might cause traffic to back up behind you. What are some of the strategies developers use to address these networking challenges?
One key technique is minimizing the number of network calls your software makes. Instead of making multiple small requests, try to batch them into a single larger request. It's like going to the grocery store once a week. Instead of every day, it saves time and effort.
Makes sense. What about dealing with latency? Is there a way to make data travel faster?
Well, you can't change the speed of light, but you can strategically place your servers closer to your users. For example, if you have users all over the world, you might want to consider using a content delivery network, or CDN. A CDN is a network of servers distributed around the globe that caches your content closer to your users, reducing the distance data has to travel.
So it's like having multiple warehouses stocked with your products located closer to your customers.
That's a great way to put it. And then there's the concept of asynchronous programming, which allows your software to continue doing other tasks while it's waiting for a network response. Instead of blocking and waiting, it can go off and do something else productive.
It's like multitasking, right? Being able to juggle multiple things at once. But multitasking can be tricky for humans. Is it any easier for software?
It can be, but it also introduces some complexity. You have to make sure your code is written in a way that handles these asynchronous operations correctly and avoids race conditions or other unexpected behavior.
Sounds like there's a lot to consider when it comes to networking.
There definitely is. And we haven't even touched on security, which is absolutely critical when your software is connected to the outside world.
Okay, let's talk about security. It's one of those things that's always in the news. Data breaches, cyber attacks, ransomware. It can feel a bit overwhelming.
It's definitely a complex and constantly evolving landscape, but there are some fundamental principles that developers can follow to make their software more secure.
Like what? Give us some tips.
One of the most important principles is the principle of least privilege. This means giving your software only the permissions it absolutely needs to do its job and nothing more.
So it's like giving someone a key to the front door, but not a key to the safe.
Exactly. If someone gains unauthorized access to your system, the damage they can do is limited if they only have access to a small subset of resources. Another crucial practice is input validation. You need to carefully check all data that comes into your system from external sources to make sure it's safe and doesn't contain malicious code or unexpected characters that could cause problems.
It's like checking your shoes for spiders before you put them on. Better to be safe than sorry.
Exactly. And then there's encryption. Scrambling sensitive data so that it's unreadable without the proper key. It's like sending a secret message in code.
I always loved secret codes as a kid. Is encryption really that foolproof? Can't hackers just break the code?
It depends on the strength of the encryption algorithm and the length of the encryption key. Modern encryption algorithms are incredibly strong, and it would take an enormous amount of computing power and time to break them.
So it's like having a super strong lock on your front door. It might not be impossible to break, but it's going to deter most would-be thieves.
Exactly. And of course, no system is completely impenetrable. That's why it's important to have multiple layers of security, like firewalls, intrusion detection systems, and regular security audits.
It's all about making your system a less appealing target for attackers and making it as difficult as possible for them to succeed if they do try to break in.
Exactly. And it's an ongoing process. As new threats emerge, developers need to stay informed and adapt their security practices accordingly.
Okay, so we've talked about stability, capacity, networking, and security. Is there anything else we need to consider when building production-ready software?
Well, we've talked a lot about preventing things from going wrong, but what happens when they inevitably do? That's where high availability comes in.
High availability, that's important. What does it mean?
High availability is all about minimizing downtime and ensuring that your software is accessible and functioning as much as possible, even in the face of hardware failures, network outages, or other unexpected events.
So it's about making your software as close to unbreakable as possible.
Exactly. And there are a lot of different strategies and techniques for achieving high availability.
Like what? Give us some examples.
One common approach is redundancy. This means having multiple instances of critical components so that if one fails, the others can take over.
So it's like having a backup generator that kicks in if the power goes out.
Exactly. You might have redundant servers, redundant databases, redundant network connections. The level of redundancy will depend on how critical the system is and how much downtime you can tolerate.
It's like having a safety net. You hope you never have to use it, but it's there just in case.
Exactly. Another important concept is failover, the process of automatically switching to a redundant component when a failure is detected.
So it's like having a stunt double ready to step in if the lead actor gets injured during a dangerous scene.
That's a great analogy.
Hmm.
And then there are techniques like load balancing, which distributes traffic across multiple servers to prevent any one server from becoming overloaded.
It's like having multiple checkout lines at a busy grocery store. It helps to keep things moving smoothly and prevent long wait times.
Exactly. And high availability isn't just about technology, it's also about processes and people. You need to have robust monitoring and alerting systems in place to detect problems quickly. And you need to have well-defined procedures for responding to incidents and restoring service.
So it's about having a plan and being prepared for the unexpected. It's like having a fire drill. You might not ever have a real fire, but it's important to know what to do if one breaks out.
Precisely. High availability is an ongoing effort that requires constant vigilance and adaptation.
Okay, so we've covered stability, capacity, networking, security, and high availability. We've talked about preventing things from going wrong and having plans in place when they do. Is there anything else we need to consider when building production-ready software?
Well, we've talked a lot about the technical aspects of building robust software, but there's one more essential ingredient that ties it all together: transparency.
Transparency. That sounds more like a philosophical concept than a technical one.
It might sound that way, but in the world of software, transparency is all about visibility, being able to see what's happening inside your systems, both in real time and historically.
Why is that so important? Why do we need to peek inside the black box?
Because when things go wrong, and they inevitably will, you need to be able to understand what's happening, to diagnose and fix the problem quickly. Without transparency, you're just shooting in the dark, guessing at what might be causing the issue.
It's like trying to fix a car engine without being able to open the hood. You might be able to hear strange noises and see smoke coming out, but you have no idea what's actually causing the problem.
That's a perfect analogy. Transparency gives you the insights you need to troubleshoot effectively, identify patterns, and understand how the system behaves under different conditions.
So how do we achieve transparency in software systems?
It starts with designing systems that are inherently observable, that provide insights into their internal state through logging, monitoring, and tracing.
Let's break those down. What's logging all about?
Logging is like keeping a detailed diary of everything your software does. It's about recording events, data points, and errors that occur as the software runs. This historical record can be incredibly valuable for troubleshooting, identifying patterns, and understanding how the system behaves under different conditions.
So it's like having a black box recorder for your software.
Exactly. But just like a black box recorder, the key is to log the right information. Not just everything, but what's meaningful and helpful for troubleshooting.
What about monitoring? How's that different from logging?
Monitoring is about getting real-time visibility into the system's performance and health. It's like having a dashboard with gauges and meters that show you CPU usage, memory consumption, network traffic, database query times, and other key metrics.
So logging gives you the historical perspective, and monitoring gives you the real-time view.
Precisely. And tracing takes it a step further by allowing you to follow a specific request as it flows through the system across multiple components and services. It's like having a GPS tracker for your data.
That sounds incredibly powerful. But with all this logging, monitoring, and tracing, wouldn't we just end up drowning in data?
That's a valid concern. That's why it's essential to have tools and strategies for managing and analyzing this data effectively. You need to be able to filter, aggregate, visualize, and search through this data to extract meaningful insights.
So it's not just about collecting data, it's about making sense of it.
Exactly. And that's where the concept of an OpsSDB comes in. An operational database specifically designed for storing and analyzing this operational data.
So it's like a central repository for all those logs, metrics, and traces.
Precisely. The OpsDB can be an incredibly valuable resource for troubleshooting, capacity planning, performance optimization, and even security analysis.
It sounds like transparency is the key to unlocking a whole world of insights about our software.
It really is, and those insights can be used to drive continuous improvement, identifying areas for optimization, addressing potential bottlenecks, and making the system more robust and resilient.
So transparency isn't just a technical consideration, it's a cultural value, a commitment to openness, learning, and continuous improvement.
Absolutely. And that brings us back to the overarching theme of this book. Building production-ready software is about so much more than just writing code. It's about thinking holistically, anticipating challenges, and designing systems that can thrive in the complex and ever-changing world of production.
It's about being a responsible software citizen.
Exactly. And it's a journey that requires constant learning, adaptation, and a healthy dose of humility.
Well said. So, to our listeners out there, we hope this deep dive has given you a glimpse into the fascinating and often challenging world of software design and deployment. Remember, building production-ready software is a continuous journey of learning, adaptation, and improvement.
Thanks for joining us on this deep dive. We'll be back next time with another exploration of the ever-evolving world of technology.
Until then, keep learning, keep building, and keep diving deep.